Good morning, or good afternoon, actually, now. My name is Auday Al-Rawe from Intrinsys Ltd. The next 20 minutes, I'll be giving you some flavor of some of the latest technology being developed by Dassault Systemes for additive manufacturing. Generally speaking, I'm going to start by giving some brief about the technology and some of the challenges associated with that, then move into the functional design, exploration, and validation techniques that we can start with that. Then the next stage is look into how we can do print simulation. And then before the end, we look into different ways of doing optimization for many of the challenging processes associated with that, and finally recap on this end-to-end solution. And I'll take the opportunity to provide a demo at the end. Just briefly about Intrinsys, just in case you haven't heard of the company. We are actually an engineering company. We are a business partner for Dassault Systemes. We have about 4 locations in the UK with about 160 people in the company. And we are also got operation in South Africa. We are the main partner for Dassault Systemes in South Africa. In terms of what we do, we provide PLM solutions. Some of you may have heard of the 3D experience, CATIA, Innovia, Delmia, SIMULIA, and so on. The other part of the business, which provides engineering services, that goes from concept through to detailed design. That includes structure analysis, design, and patent product and component tools. That's really just general introduction about the company. Let's move into the first part, the technology. We've had some very nice, challenging presentation earlier on about additive manufacturing. We all know the story, 3D printing, how it's developed to the stage where it is now. However, it's not all good, obviously. It doesn't come easy. So there are so many challenges associated with additive manufacturing. So these days, a lot of people trying to use additive manufacturing for grade type prototyping and tooling application and so on. And we've seen a lot of them being explained earlier on. I don't have to spend so much time about telling you the advantage of additive manufacturing. These are some of them. It's become more obvious to most people these days. So multiple part consolidation, access to complex geometry, freedom, reduced tooling cost, bespoke, lightweighting, and probably the most important, faster to market. So, what are the challenges? Material properties, very challenging. Why? Because manufacturing material properties is different from material properties that you put in the beginning. Secondly, cracking and failures. A lot of people who are actually done additive manufacturing realize this is a familiar story where you have cracking at the end, which means you end up throwing the part after it's been printed. Distortion and tolerance issues. There's so many problems associated with it. So it's one of probably most challenging thing to get your design right is to get it with less distortion and so on. So these are challenges, and also there's the additional to the new material, different new machines. You know, every day, every month, you see a new machine coming to the market, different processes, and so on. All these things are challenges for the industry. And then on top of that, obviously, certification. We all know certification are the early stage. So unlike the standard fabrication processes, this is really, really early. But the good news is the STM Committee F42 is working on defined standards and is going very well. So, how to address these challenges? The first part is to generate a functional design. We heard in the previous presentation about topology optimization, and that's basically what it is. We have additive manufacturing offers the opportunity to look into the concept design, more flexible. Before, you're restricted to manufacturing processes and so on. Now, you have the opportunity to actually be more inventive. You know, look into make more conceptual design is more attractive, less weight, stiffer, and so on. So topology optimization offers that. Lattice modeling, again, in the previous presentation we heard about lattice modeling. It's an excellent way of reducing weight and making the structure stiffer and so on. Again, there are these days latest tools in the market allows you to optimize this lattice modeling, which was very challenging in the past. Calibrate the material. Material is the main part that drive the result at the end. So it's important to calibrate the material, and we're going to look into the methods these days that people use for that, doing that. Being able to simulate the print process. The print process is different to the standard fabrication. So how do you print? How do you make sure you actually simulate it correctly? And also, how do you optimize the processes associated with that? That could be the angle of printing, could be the laser path, printing speed, so many of them which we're going to go into. And finally, in-service performance. It's important to evaluate how the manufactured part will perform once being assembled in the actual part. So let's look into the first part, functional design. So this is basically at the concept stage. So please look into this as like we are looking into the concept design. So the tools from Dassault that have been introduced recently within 3D experience allows you to do that within the CAD environment. Most of these tools used to be considered advanced and only skilled people use it. So that's why it's been introduced into a CAD environment to allow the average designer to actually use them and have access to it. So it takes into consideration complex behaviors such as sliding contacts, bolts, modeling, and so on. And it's all within the same environment. Here's an example of this part, basically. Once, we're going to look into this, by the way, in the video later on, which will be more obvious. Once the designer defines all the boundary condition, loading, and so on, then he can freeze certain parts, such as the holes and so on, and then define your manufacturing restrictions, and the software will automatically generate the best topology for that particular job. And the best part out of that, if I go back to this actually, is that the challenge most of the time with topology optimization tool is how do you get that part once been optimized back to CAD? Yeah. You export it to STL or a different format. You take the element patch into the CAD software, and you spend a long time trying to clean the geometry and all that before you can use it. With this tool, it's a click of button, basically. As soon as you have the topology optimized solution, you end up with the geometry straight away. And then it gives you the option where you can do a trade-off, where you could try different material, you can define different options and so on. And then you can have different designs, and it presents you, maybe you can define what's your best criteria, such as mass, stress, displacement, and then you can choose from them based on the requirement. Once you've done that, then within the same environment, you can then go and re-smooth it. In this case, as you can see, it's not very smooth, so the designers now is going to go and resurface it, use the tools available within the system to help him get a better surface that way. Once, in this case, there's a symmetry, so he's working on a particular, only a quarter of that particular geometry. And then once we optimize that quarter, then we can mirror it and copy it across to get the full geometry in there. All that is really, really difficult in the standard tools. It's because you have to you spend hours and sometimes days cleaning geometry once it's been optimized in the optimizer. And the next part, obviously, if you wanted to do additional topology optimization, such as shape, maybe shape optimization, or look into lattice modeling and so on, and that's basically it. So in terms of the conceptual design, that's basically the process associated. This is just to show you why people use lattice modeling. It allows you to have a 40% reduction, up to 40% reduction, sometimes in weight, and gives you better stiffness and so on. There are different ways of lattice patterns. These are just some of the most common lattice shapes. Just to summarize the first conceptual design, basically we haven't done any printing simulation so far. This is just a summary of the conceptual design. So we start with our concept. We put our boundary conditions and FEA, and then define our restrictions, such as manufacturing restriction. We freeze the parts that we would like to freeze. So we tell the software, don't touch these. And then we end up with a concept, and then take that into the CAD system, which is actually, in this case, in the same environment. Then revalidate it. We need to revalidate this, and to make sure that it's still with no hot spots and stuff like that. And then, again, we've shown you how to do resurfacing and so on. The opportunity to do extra optimization, such as parametric, such as a lattice or shape optimization, and again, do revalidation, do that. All that is part of the conceptual design process. Okay. So that's the first part. Next part is how to do the print simulation. The way to do that, we need to capture the physics, the material, the process specifics. We need to look into the stress and simulate the stress and distortion, which is the most challenging thing. With any additive manufacturing process, the most challenging is actually the development of heat in them. So how do we simulate that? We need to calibrate the materials, as I said earlier on. And then finally, optimize the process. This is just something to show that the technology for building layers and so on is not necessarily new. This is just something being done in Abacus for many, many years. Allows you to automate the process of welding and development of residual stresses and so on. So basically, the same concept is being used in additive manufacturing here, where we layer the elements and use the element starts in an inactive mode, and then it becomes active according to the hardware code, basically. These things, I don't know if you can see it, we can see the element is developing according to the laser path, and it just builds up gradually layer by layer. The reason for that, then it allows us to then capture the physics, allows us to be able to capture how the heat is developed from one layer to another. Then we can then do thermal stress analysis in order to capture the deformation, distortion, and so on. Here's an example of how that part is being printed. It's actually simulated before it's being printed in order to see the effect of the temperature development, and then maybe stresses in order for us to predict the residual stresses and so on. You can see, I mean, this particular part is probably about 1,200 layers in there. So it's important to capture how it's being printed. And then the direction of that laser path, the angle of printing, all these things affect that particular thermal stress development. So how do we bridge the gap between us designers and manufacturers? We know the most challenging part for any designer with additive manufacturing these days is the geometry he's going to design is different to the actual geometry is going to be manufactured due to the residual stresses and so on. The material he's assumed at the beginning is going to be slightly different, or probably even a lot different from the material that's going to be manufactured at the end. So we need to bridge that gap. We know with the additive manufacturing processes, there's so many processes. You have powder bed, binder jetting, directed energy deposition, and so on and so on. So it's important to capture the right process and so on. So we know the material gets affected by the process. For example, for composites, particles of fiber are affected by the extrusion of the process to make the directional properties of material different. For metals, the melting, solidification will make the material actually have different stiffness and different strength. So how do I address this? Multi-scale modeling. Most of us have worked, if you are a designer or an analyst, you probably worked in that mid-range or maybe the top part of that particular slide. But these days, multi-scale modeling allows us to go into the bottom side or up, and then you can deal with things like the microstructure or model or simulate the molecules or even the electrons behavior of that particular material. That will help us then to predict what sort of material that part is going to be printed with and so on. It's just something mentioned about the BioView, which is a new brand through acquisition by Dassault Systemes, which allows us to, it's a material studio, which is an environment for virtual screening and property prediction of a range of materials. So in terms of multi-scale material, I'm not going to get into so much details. It's the concept of RVE, which is representative volume element, which allows you to model the microstructure of that material and then homogenize it across the structure, which allows us then to predict the material property. This is an additional way to testing physically and so on. So we've done conceptual design, we've done print simulation, but how do we optimize these processes? We've seen so many different challenges. So we need to look into the optimization of these processes. In terms of optimization, the angle of printing affects the process at the end. Could be the topology optimization, we mentioned it earlier on. Support structure, especially for metal additive manufacturing, it's so important to have the right support. You can't just print on nothing. Otherwise, you'll end up welding the plate, the actual part on the plate. So you have to have the right support to act like a heat sink for you. So again, different support needs to be optimized. And finally, the laser path, which is the most important out of that. How is that laser path going to go in each layer? Is it going to go 45 degree, 90, 0, and so on? So how do we do that? It is a tool within Dassault Systems that allows us to do the design of experiment, the OE type of thing. And then you can capture all these processes automatically, rather than do them manually. In this particular example, we're trying to automate the process modeling of printing, for example, and trying different printing time in order to see which one will offer us the best possible temperature and development and best deformation. In this case, we've highlighted the 5-hour, for example, it will offer us ideal solution in terms of less stresses and less distortion. This is just to show the effect of support. When you put support, obviously, we'll be able to simulate the spring backs and so on, because all these supports need to be detached from the geometry when it's being printed. So after you be detaching this, what will happen to the geometry? So you can simulate all that in advance, rather than print them and find that the deformation is too bad. So just to recap, before we go into the video, so we started with a concept design, allowed us to get into a optimized geometry. We revalidated it. We looked at the different options. We resurfaced it. Then we did more refinement by lattice modeling or shape optimization. Again, do the revalidation before we do the print simulation. Then we get into print simulation, where we define the laser path, define the support, look into do the print simulation in order to be able to predict thermal stresses and so on. And at the end, allows us to be able to have an end-to-end solution so we can simulate the printing before it's actually printed, rather than print it and took 3-4 days and find that you're going to throw that part away and start again. This is just to show the different, the one on the right-hand side, the actual part, before it was printed in using additive manufacturing. And you can see in here, there was about 40% lighter product being developed in there, and 10 times faster, which is more important, especially for aerospace and other industry. Okay, so that's the time to go to, sorry I've gone very fast, just restricted to time, but maybe I've got enough time to go through the video, which basically summarizes what I've just been talking about. So we start in here by going through the conceptual design. In here we're seeing all the geometry modeling features within Dassault Systemes product. You can see the designers now is basically defining features that allows him to consider that as a concept. He doesn't have to worry so much about that. He just needs to define the holes and freeze the hole. You'll see later on he'll be able to define where the parts that he needs to freeze. In this case, you see you can actually start with the parts from the assembly, or you can start from scratch like here and then plug in that in the assembly. Once you've done that, basically, then you can choose the material property, which is probably defined by another person more experienced. Once you define your material properties, then you can define your loading. It could be static, frequency analysis you need to do. And in this case, we're trying to freeze the parts that we don't want the software to touch, basically. These are critical parts that we're going to put maybe bolts, or it's going to go through a bar or whatever. And next, then obviously we generate the mesh. What do you see? If you can notice the right-hand menu, this is designed for a designer, basically. As I said earlier on, it's very challenging. Most of these tools used to be considered advanced and very need skill. Now, the designer are able to access. Why? Because it guides him. Every time you finish one step, it takes you to the next step. So now we're defining our loads, we're defining our support. It could be part of an assembly, actually, but in this case, it's just one part. And now we're going to put the bolts with the preloading. We started with one bolt. And once we've done that, then we can copy it across. We don't have to do it again. That's being copied now. And then basically we define our targets. What are our targets? Minimum weight, better stiffness, and so on. Once we've defined our targets, then we can ask the software to do the optimization. Again, we're working in one environment. We're not going from one software or from one tool to another. Okay, so now we are at the stage where we are going to run the analysis. And now we'll be presented with the results. And you can see all the cases in there. You can go browse them, but obviously what you want is your optimum solution. In this case, you've defined your target, so you know your optimum solution. And then once you have that optimum solution, this is what I said earlier on. This is the best part in my case. You click on a button, you generate geometry straight away. This is not elements, geometry. And that geometry, this is geometry now, can be taken in the same environment to do resurfacing and smoothing and so on. Obviously in here, what the user is doing revalidation. So once we've done that, we're doing revalidation. And the beauty about this, again, all the loading, all the supports are in there. You don't have to reapply it again. Just generate the mesh, apply maybe additional loading and so on, and revalidate it. And see, obviously, the product is not smooth enough, so the user is going to go and resurface it to optimize that. But before doing that, he's just going to do a trade-off in order to look at different scenarios. So maybe he's trying different properties, different processes, and so on, in order to help him identify the best solution. And in there, and he'll choose a particular design before going into the next step. Right, we've chosen our design, and we've done that part, so I'm going to go through it quickly. You've seen it earlier on. So we're going to resurface it. Once we're happy with the geometry, then we can go to the next step. Maybe you do either shape optimization or lattice, as I said earlier on, that you've seen in the video. Okay, all that is part of the conceptual design, okay, before doing the print simulation. So, next. You see in here there are different parts. This is the actual legacy part. This is with milling, with additive manufacturing, in a different in terms of weight and bite-to-fly ratio. What you see in here, basically using the digital manufacturing tools, Delmia from Dassault Systemes. This is based on the Renishaw machine, basically, and in there the user is doing nesting. So you can see the reason why printing more than one part. While you're printing, you want to print as many as you can, because when that printer is going, you need to make it more efficient. So in there, the user is just position that part, and then the next stage is to define support. As I said earlier on, we have to define support, otherwise it'll be welded on the plate. So again, from the menu, choose different support. There are different support options available. And you'll see that in a few seconds. Okay, once we've defined one support and we're happy with it, then we can copy it across the other parts. You can see the supports are very thin, basically, because that needs to be detached later on using the standard fabrication processes, basically. So it needs to be as thin as possible. And the next step, obviously, copying across. And now our target is to define the laser path. So we need to decide, out of all these layers that we're going to be printing, what sort of angle we're going to use, and so on. So you can see, I don't know if you can see it clearly in here, there's actually lines defining the angle of that particular laser. And we could choose what angles we want, different layers. And then the slider shows that's the actual angle in each layer. Once we've done that, we need to go to then we can go to the physics tool. And now all the supports, all the geometry in there, remesh it. And next, we put our loading, boundary condition, and so on. And we know, because we already defined these laser path angles and so on, now we get the results. In this case, it could be deformation, it could be stress development, thermal stress analysis, and so on. Whatever it is, allows us to predict. At the end of the day, we want to see how much residual stress has been developed, how much distortion being developed through that, and so on. So we are able to simulate that process before it's been printed. And that is basically according to how we've done the printing. So it's actually linked to the way we've defined the laser path and so on. Okay, at the next stage. And now, obviously, we're looking into process optimization. We heard about different angles could affect the process, maybe laser path, so many different processes. We don't want to do that manually. So there's an automated tool within the software that allows you to automate that. And then you can look for the best optimized angle, best optimized maybe laser path, best support, and so on. And you can see in here, just showing you the different laser path and so on. If you stop the video in here. And finally, if I can just play that. We look at the final part, which we missed it. If you look at the top right-hand side of that picture, you will see that the user is able to predict how much consumable he's going to use, and also be able to predict how long the print process is going to take as well. It's all that part of the simulation. Okay, thanks very much. Questions? Questions? Question?
So, how long does it take to do a simulation for the part? I realise that's going to be geometry dependent, but is it competitive with manufacturing the part? Because quite often, the consideration for the company is not necessarily going to be, can I say, material-wise simulation. It's going to be how fast can I determine the end result. So is the simulation competitive with manufacturing?
Yeah, it's a very good question. I mean, I have asked designers in the past, and I said to them, how long does it take you to actually set up the machine and all that, trial and error? You know, sometimes it takes them 1 month to actually get the setup right, sometimes for certain geometry. So that takes a long time. Yes, it's an investment on time and all that. It depends on geometry and all that. But at the end of the day, once you've simulated that part, you set your processes as well, you can reuse it again. Yes, you may spend time at the beginning learning, skill yourself, set up the processes, but then you can reuse it again and again. And instead of taking maybe 2 days or 3 days to print something and find out it's going to be wrong anyway, you may as well spend half a day or a couple of hours doing the simulation, and then you can predict that rather than print it. Yeah. Anything else? Okay, thanks very much.